Hi, everyone. My name is Dr. Paxton Frady. I'm a researcher at the Neuromorphic Computing Lab at Intel and also affiliated with the Redwood Center for Theoretical Neuroscience at UC Berkeley. And today I'm going to tell you a little bit how some of our efforts into encoding manifolds in spiking neurons may relate to observations we have of the hippocampus. So I work at Intel. I'm not really going to be telling you too much about any Intel products, but just there's these legal requirements Intel has for talking about research. And I will be a little bit telling you about the Neuromorphic Computing Lab. And our efforts are to try to use insights from neuroscience and artificial intelligence to enable application of this neuromorphic hardware. And so these is a computer chip that can simulate integrated fire neurons and in hopefully a very large scale and energy efficient way. And we think that there's a lot of opportunity for new computing applications. Of course, we're definitely looking into artificial intelligence with neural networks and deep learning, but one thing that is emerging is that there are some weaknesses to deep learning. And so, for instance, if you apply these very simple geometric transformations to objects, you can fool deep learning neural networks. But to us and to our brain, it's almost trivial, this problem. And so we're hoping to look at neuroscience and other ideas in machine learning and how to enable new types of neural network machinery in order to help artificial neural networks deal with basic transformations like changing the pose of an object. So we have been developing our ideas starting from a groundwork where we are thinking about distributed computation with vectors. And from this structured groundwork, we believe we can build much more scalable algorithms. And the short story of this framework is using ideas based on random indexing to represent and encode information into high-dimensional vectors that may or may not resemble neural activity. And so the key idea is that symbols are just represented by random directions in this vector space, and that there are a few algebraic operations that allow you to manipulate these vectors in ways that might match the outside world, or that allow you to build data structures inside of these vectors. And there are also ideas in neuroscience about how hippocampus may also be serving as one of these index structures and generating neural activity patterns that are unique for an animal being in a certain context and in a certain location that then the brain can use to associate the context with other neural activity patterns going on throughout the brain. So in our efforts to try and understand how to encode information with these data structures with high dimensional vectors, we realized there was a missing link into how to represent continuous values, which you often need to represent smooth manifold structures, like, for instance, your location in the environment is a continuous value. And if you want to index these types of continuous numbers, you need these two key properties. For one, you need vector representations of points that are far apart to look different from each other. But for points that are close together, you want their vector representations to be similar and to transition smoothly. And so we realized that there's this way of performing these type of functions by creating high dimensional vectors of complex valued entries. And this property that these vectors have is very interesting if you just exponentiate their values. So every entry in the vector is a unit magnitude complex number with just a phase. And we can multiply the phases together to spin these vectors around in a way that's such that, like, this vector v squared looks nothing like the vector v. But in the continuous domain, this happens can happen continuously, and so this just amounts to spinning these vectors around, spinning the phases around these vectors, and just doing this has this property of distinguishability and smoothness that we can use to represent smooth manifold structures. So what happens is basically as if you compare the vector representation of x to the fifth to x to the little x, as little x moves along this x-axis, you see this kind of characteristic similarity kernel emerge. And so x to the fifth looks, of course, like x to the fifth, but x to the fourth looks nothing like x to the fifth, and neither does x to the sixth. But there's this in-between space that looks approximately like a cosyne, and you can use this to essentially interpolate through these different unique-looking vector patterns. And essentially, this is creating this geometric arc, which visits different orthogonal vectors in sequential order, and approximately looks like interpolation as you go from one vector to another. And so why this is useful for representing space is because we can then use these VSA operations to come up with an indexing code for two-dimensional space or even higher dimensional space by essentially just doing this exponentiation trick with these complex valued vectors and then multiplying them together to like encode more than one dimension. And so if you wanted to come up with a representation of a two-dimensional space, you would just say take the mouse's location is the x and y coordinates, use them to exponentiate these complex vectors, and that would give you a code for the two-dimensional map. And what's interesting is that you can then translate or do something like path integration by updating this vector. So if the mouse moves a bit delta x, then you can take this random vector, raise it to the delta x power, bind it to your sort of representation of your current location, and you'll come up with a new representation of your new location. And so by doing this iteratively, you would essentially implement a path integration algorithm. Now, there is a lot of machinery and different versions and flavors of these vector architectures that look more or less like neuroscience. And so some of the steps we've been taking to bring it closer to neuroscience, you know, is just like thinking about different ways of implementing these sort of same ideas. And so I would just point you very quickly to two papers that we have that are towards this effort. The first is about how we can use spike timing codes to represent these complex valued vector states and perform the operations in a biologically plausible manner, as well as a new framework for performing these random indexing operations on sparse vectors. And so we have this paper about how to do this with sparse vectors. But long story short, if we take these spike timing code and sparse encoding of these manifold structures, and then we kind of plug it into a model of a mouse just exploring an environment, a lot of the essential properties that people record from hippocampus just emerge. And so here we see just the mouse exploring a two-dimensional box, and and this is the evoked neuroactivity if you just follow the premise of this model. And so then you can sort of compare that potentially to, you know, what we record in neuroscience, and you know, simple things like place cells emerge, but also you get this phenomenon of phase precession. So since we're using this oscillatory framework of spiking neurons to represent these complex values, in this code, you do in fact see cases where as a mouse runs through a receptive field, the spikes precess relative to the background oscillation. Now, there's lots of things about the model that don't quite fit the hippocampus literature, but what's really exciting to maybe to neuroscience is a proposal that perhaps what's going on in the hippocampus is a bit more complicated than just representing a two-dimensional location in space. For instance, we already see evidence that place fields are direction selective. So of course, if a mouse is running down a one-dimensional track, it's typically the case that the place field, the neuron for the mouse running from left to right is different neuron, but in the same place when the mouse is running from right to left. And so something like the head direction of the animal might play a role also in the representation of hippocampus. And so you can take this random indexing idea and extend it to incorporate more variables. For instance, the view and place of the mouse in a particular context. And so Here I try to like explain how this more complex version of the model can also give you some insights into more modern recordings being done in the hippocampus and other brain regions where thousands of neurons are potentially being stored all at once, recorded all at once. So you can think about these different dimensionalities that emerge when you have these recordings. And so the first is like the neural dimensionality. So that's just how many neurons you pick up. And this is typically, we use these high dimensional vectors as our representation. So this is how many neurons you have in your vector. But then you might have something just called the tiling dimensionality. And so depending on exactly how you design these models, you'll actually grid out the space where essentially one grid length tells you you've gone far enough for the vectors to look different. And so if you kind of understand how this tiling space plays out, then if you do a simple analysis on these the neural activity patterns that emerge from this model, like principal components analysis, you'll extract then you'll have significant eigenvalues up until the tiling dimensionality. So depending on how the space is tiled by this code, you can extract that dimensionality through something like principal components analysis. And of course, then there's the manifold dimensionality itself. And so this is actually these small variables in the exponent where these are your true degrees of freedom, your translation up and down and left and right, and also your viewing angle. And through algorithms like isomap, you can extract then the low-dimensional manifold from this neural activity, which is really entangled in this indexing code. And so it becomes more complicated and a little bit trickier if you have more complicated, higher dimensional representations in the hippocampus. But with the right algorithms, you can pull out then these low-dimensional manifolds. So that's all for my talk for today. There's some links to a more detailed talk online, and just message me if you have any questions. Thank you.